From our own backyard in the solar system to the farthest reaches of the cosmic ocean, the universe has always been a source of wonder and intrigue. Back in the day, ancient stargazers puzzled over comets and pondered the secrets hidden within the stars. As time went on, we unlocked many of these mysteries through science. But now, armed with powerful telescopes and cutting-edge technology, we find ourselves faced with a whole new set of questions that push the boundaries of our understanding. How do galaxies come into existence? In simple terms, it's all about gravity. When the universe was in its infancy, matter wasn't evenly distributed. Regions with slightly higher density attracted more matter, gradually growing in size over time, while emptier spaces became even more barren. Despite the universe's expansion, these denser regions pulled matter together, forming the building blocks of galaxies, including our own Milky Way. To understand this cosmic ballet, cosmologists turn to massive computer simulations, such as the renowned Millennium Run, conducted by scientists at Durham University. Remarkably, astronomers can recreate an entire universe within these simulations. By comparing the resulting galaxy distribution to what we observe in the real universe, scientists gain valuable insights. One prevailing model suggests that the bulk of the universe's matter consists of elusive dark particles that interact minimally with ordinary atoms. According to this model, galaxies and galaxy clusters should be linked by intricate filamentary structures, a notion supported by certain observations. However, there's a complication. The models also predict that large galaxies should be surrounded by numerous smaller ones, yet these aren't always observed. Additionally, the formation of the first massive galaxies shortly after the Big Bang remains a puzzle. Thus, while our current understanding offers valuable insights, it's clear that the picture is not yet complete. The uniqueness of our solar system. Is our solar system one of a kind? This question sparks intrigue, especially considering that until the mid-1990s, astronomers were unaware of the existence of other solar systems. While a few planets were discovered orbiting pulsars, dense remnants of stars emitting lethal X-rays, the idea of planets around sun-like stars remained elusive. Has the mystery of our solar system's singularity been unraveled? In a sense, yes. We now know it's not alone. Astronomers have identified other sun-like stars accompanied by planets, thanks to the diligent work of exoplanet hunters. These discoveries include peculiar exoplanets like hot Jupiters, which migrated inward, disrupting the orbits of other planets in their systems. The chaotic dance of planetary billiards resulting from such migrations suggests that Earth-like worlds in these systems might struggle to sustain life. This realization hints that habitable planets might be rarer than previously thought. However, our current telescopes have limitations. They cannot yet detect solar systems akin to our own. Yet, future advancements hold promise in unveiling such systems, potentially revealing that they are more abundant than imagined. Indeed, nature tends to produce multiple iterations of phenomena, suggesting that while our solar system may be uncommon, it likely isn't the only one of its kind. Until we discover a solar system resembling our own, the question of its uniqueness remains unanswered, keeping astronomers and enthusiasts alike captivated by the mysteries of the cosmos. Is Isaac Newton's theory outdated? Moving on next, we encounter a thought-provoking inquiry. Was Isaac Newton mistaken? While his theory of gravity has successfully guided spacecraft to the moon, it falters under extreme speeds and intense gravitational fields. Enter Einstein's general theory of relativity, offering a more comprehensive framework. It accurately explains phenomena like the gravitational bending of starlight, the orbital decay of binary pulsars, and the curvature of space-time around black holes, making it the preferred model among physicists. But why entertain doubts about Newton's theory? History suggests that scientific progress often reveals deeper truths. Physicists may uncover subtle effects hinting at a superior theory of gravity. For instance, the perplexing deceleration of spacecraft like Pioneer 10 and 11, exceeding what's predicted by gravitational forces alone, has spurred speculation about new physics. Despite passing numerous rigorous tests, general relativity isn't exempt from scrutiny. Scientists continually subject it to meticulous examination, using spacecraft data and astronomical observations. Thus far, Einstein's theory has withstood scrutiny admirably. Yet, the quest for deeper understanding persists as physicists explore the possibility that general relativity may not be wrong per se, but rather incomplete. Life beyond Earth. No matter how improbable the emergence of life on Earth may seem, the vastness of the universe suggests that there could be numerous other inhabited planets scattered throughout the cosmos. Consider this, with approximately 100 billion galaxies in the observable universe, each containing tens of billions of stars, many of which likely host planets, the potential for life-bearing worlds is staggering. Even if life arises on only one planet out of every trillion, the total number of such planets could still be on the order of 1 billion. However, the tantalizing question of extraterrestrial life remains unanswered, awaiting discovery. In our own solar system, several locations show promise for hosting microbial life, including Mars, Europa's subsurface ocean, and possibly Enceladus, a moon of Saturn. The detection of Martian bacteria would revolutionize our understanding, affirming the prevalence of life in the universe. Yet, despite extensive exploration, no conclusive evidence has been found. However, ongoing efforts to analyze exoplanet atmospheres offer a promising avenue. The presence of significant levels of oxygen and methane in an exoplanet's atmosphere could signal the existence of life. While the search for microbial life focuses primarily on nearby planetary systems, some scientists explore alternative methods, such as SETI, to detect potential extraterrestrial civilizations through radio communications. However, this approach assumes that the evolution of life inevitably leads to intelligence and technology, a notion not universally accepted among evolutionary biologists. The Fermi paradox adds another layer of complexity to the quest for extraterrestrial life. Despite the seeming abundance of potentially habitable worlds, the absence of observable alien civilizations raises intriguing questions about the nature of life in the cosmos. For now, the existence of extraterrestrial life remains a tantalizing yet unproven hypothesis. As long as conclusive evidence eludes us, the search continues, fueled by curiosity and the insatiable desire to unravel the mysteries of the universe. Could the cosmos have diverged? Our material cosmos is a realm governed by elementary particles influenced by 4 fundamental forces of nature. Physicists meticulously measure properties of particles, explore the behavior of gravity, electromagnetism, and nuclear forces, and determine constants such as the speed of light. Yet, the origins of these values remain a profound mystery. Why does the universe possess its particular configuration? And could it have been otherwise? One thing remains abundantly clear. Tinkering with the cosmic controls can have drastic consequences. Even minor alterations in particle mass or charge, or slight adjustments in the strength of natural forces, could result in a barren universe devoid of stars, planets, and life. It appears as though the intricate balance of nature has been finely calibrated to foster complexity, almost as if the universe has been tailored for the emergence of life. This realization presents a perplexing puzzle. If the universe's fundamental properties arose from random chance, it seems astonishingly fortuitous that the outcome would be so precisely tuned. Yet, if a theory of everything were to dictate a singular universe, it raises questions about why this unique solution must necessarily harbor conditions conducive to life. Enter the concept of the multiverse. In this theory, our universe is merely one among a vast array of potential universes, each with its own set of natural constants, particle properties, and force strengths. While this notion may seem far-fetched, history reminds us of similar skepticism toward ideas questioning the uniqueness of Earth, the Sun, and the Milky Way. In a multiverse scenario, the existence of myriad universes ensures that all conceivable combinations of constants and properties manifest somewhere. Consequently, we find ourselves in a universe conducive to life's origins almost by necessity. However, not everyone finds solace in the multiverse concept. Some astronomers argue that its untestable nature renders it outside the realm of science altogether. Nonetheless, as we grapple with the enigma of universal constants, the notion of a multiverse continues to spark debate and intrigue among scientists and philosophers alike. The validity of cosmic inflation. Determining whether inflation actually occurred is no easy task for cosmologists. The theory proposes that inflation was a rapid and exponential expansion of the universe in its early stages. In just a fraction of a second, the universe purportedly doubled its size 100 times over before settling into the slower expansion phase we observe today. But did this dramatic event truly take place? For cosmologists, inflation provided a compelling explanation for a perplexing puzzle. How could the universe exhibit such remarkable homogeneity if distant regions had never interacted? The theory posits that before inflation, the universe was incredibly small, allowing any irregularities to be smoothed out before expansion. Additionally, inflation offered an explanation for why the large-scale curvature of the universe appears to be flat. Despite the elegance of this theory, direct evidence for inflation remains scarce. What is the universe made up of? Alright, let's now delve into the fascinating realm of cosmic composition. Understanding what makes up the universe is like piecing together a complex puzzle, and it's a puzzle we're still working on. So, what's the story? First off, we have the matter we're familiar with, the stuff we see every day, like atoms, molecules, planets, and stars. This makes up just a tiny fraction of the universe, about 5% to be exact. But even within this 5%, most of it is invisible to us. Only a tiny sliver, roughly 0.4%, is made up of the stars, planets, and gas clouds that we can observe with telescopes. Now let's talk about the dark side. Dark matter, and dark energy. Dark matter is a mysterious substance that doesn't emit or interact with light in any way we can detect. We only know it exists because of its gravitational effects on galaxies and light. It's like an invisible force holding the cosmos together. Dark matter makes up about 27% of the universe's total mass energy content, making it a significant player in the cosmic drama. And then there's dark energy, the real cosmic wildcard. Dark energy seems to be causing the universe to expand at an accelerating rate, pushing galaxies farther and farther apart. We're not entirely sure what dark energy is or how it works, but it makes up the lion's share of the universe's mass energy content, about 68%.